My name is David Sankel. I am a principal scientist at Adobe in the Software Technology Lab. And this talk is called Under the Hood. We're going to talk about assembly language, system calls, hardware. So basically, you take C++, you open that sucker up, you see this stuff, okay? And I took this idea from Sean Parent's talk. He had cars all over his talk, so I had to put a car in my talk. All right. Does anybody know what this is? I mean, what is this a screenshot of?
Compiler Explorer.
Compiler Explorer. Very good. Okay. So what happens in a ton of talks is they throw up Compiler Explorer, and then they say, hey, you see the thing on the right, and they kind of hand wave a little bit, and you just kind of like smile, and you look to the person next to you, and you're like, yeah, I think I understand it. No, I don't really understand it. And then they go to the next slide, and you're like, oh, thank God, right? So the goal here is to get us to the point to where we can look at the stuff on the right-hand side and kind of understand what's going on. We're not going to go like super deep. That would require more than time we got, but that's the general idea. So just looking at this code here on the right, there's something, even if you know nothing about assembly, you can tell something about this code. Does anybody see it? Yeah, you're right. Right, you take a look at this thing of whatever kind of random language that is, and you look at this one right here, and they're the same thing, okay? Great, you guys are already getting better at assembly. Well, hey, you're advanced. You're advanced, but that's true. Okay, so we're looking at the code on the left-hand side. All right, so these are two functions. One's called chain, one's called unchained. What they do is they add these four integers together. And I was in a presentation where somebody showed code like this and said, the second one is X percentage faster than the first one, okay? Because there are parentheses in there, and it does something faster. But we, as assembly experts, have already determined that the assembly is the same for both of these, right? So that goes to a very important maxim, which all of you know. Don't make performance claims without benchmarks. But there's a little caveat to that. Unless you can show identical generated assembly, in that case, go ahead. You can make claims. It's the same speed. Okay, good? Thumbs up? All right. I don't see a thumb. I see a hand up. What does that mean?
I have a question.
Okay, I knew that. What's your question?
Could the assembly be different for those if they were floating points?
Yes, but we're not going to talk about that.
I think that also assumes that both assemblies have the same alignment.
Okay, alignment. All right, look, there are experts in the room. This is me waving my hands. Same assembly. All right, moving forward. All right, what is manual memory management? All right, if you look it up on Wikipedia, manual memory management is the usage of manual instructions by the programmer to identify and deallocate unused objects or garbage. So the idea of allocating something, and then if you have to deallocate it manually, they're calling that manual memory management. But that's really not what we're talking about in assembly when we talk about manual memory management, because in assembly language, you need instructions to move information between the RAM and the CPU, right? In C++, you don't really get exposed to moving stuff to the CPU and moving stuff outside of the CPU. So the model that you get with assembly is you have your RAM on the right and you have your CPU on the left, and those are all little like storage slots, okay? And you transfer data between your RAM and your CPU. So here we're moving 4 to the CPU. You can't read that because it's infinitely small. Here's moving another piece to the CPU. Once you have your stuff in your CPU, generally speaking, you do an operation in your CPU like arithmetic, which populates another piece of memory in your CPU, and then you move that back to the RAM. Got it? This should be a review, right? We all know this. That's how it works. Now, I didn't put cache in here because generally when you're programming an assembly, you don't have visibility that there's a cache. That's behind the hood of assembly even. You just get this model of the things on the left and the things on the right. So these things on the left, by the way, these are called registers, right? We got this. It's good. Okay, so let's look at the Intel 8008. This is prior to Intel x86. This is what it looked like. And these are the registers. You have A, B, C, D, E, H, L, and PC. And that's it.
Well, right at the top.
Right, well, it's perfect. The registers in this CPU are 8-bit. And the A actually stands for something. It stands for accumulator. So in these like old chipsets, some of the registers were special because there would be certain instructions that only worked with that register and made it better for the silicon or something like that. But yeah, you'd be wondering like, where's the H and L coming from? So with this old computer here, if you want to address more than 255 elements of 8-bit memory, you're going to have to, if you want to get like a 16-bit memory address, you're going to have to use 2 registers. So the high order byte and the low order byte were for accessing that 16-bit address space. And then you had your program counter there on the bottom, and that's how it worked. And everything was grand. Then after that, they decided to create the Intel 8086. Now, unlike the Intel 8008 that came before it, the Intel 8086 took off in such a way that even our most modern processors can run stuff that ran on the 8086, okay? They all kind of are backwards compatible in that way. And this is what it looked like. So what you'll notice is we have these weird split registers on the left. Because this is a 16-bit processor, they wanted to be able, like if you were going to do like 8-bit computation, you can get like the left half and the right half of those 16-bit registers. Okay? So here in this case we have DH and DL, and what that stands for is D high and D low bit registers. Make sense? Cool. What does the X stand for? DX is a 16-bit register, and X is a placeholder. Like 3.x means all the versions 3 of something, or x86 means all the different kinds of x86 chips, like 30 or 8386, 8486, whatever. So that's what X meant there. It meant both the H and the L. Kind of cute, right? Until like time passes. And all these things, all these registers had names. So we had the accumulator, the base, the count, the data, and then on the ones on the right. But there were, again, like there were certain instructions that only worked with certain registers. They weren't all completely general purpose, although there was some general purpose instructions that would work with any of them. The stack pointer and the base pointer on the top right, those two got added because this idea of putting some like variables on your stack and then calling another function which puts more variables on the stack turned out to be a good one, like how we call functions. So that was a neat feature that they added to the 8086. And then you have source index and destination index. What these were used for are string operations. So your source index would point to one string and your destination index would point to another string. And there would be code to like copy from one string to another using the source index and destination index. And then you have your instruction pointer, which points to the current instruction that you're executing.
Base pointer was also used for segmentation, right?
The comment was, base pointer was also used for segmentation. I don't have to repeat the comment. Okay, I'll stop doing that. So there were segmentation we're not going to talk about like in this talk. So I don't want to get into the details of it. I'm going to pretend it's because I have other material to get to, but the reality is I don't really understand segmentation yet. So, but I'll pretend. All right, so then things got bigger. They had the 8386 came out. Now, we're not talking 16 bits, we're talking 32 big bits, okay? And they needed to figure out other names for these things because, you know, AX was already taken. So they said, all right, we'll call this the extended AX register. That didn't age very well either. But essentially, you still have AX available for the 16 bits on the right, and you still have AH and AL if you want to get the byte. But if you want to get the full 32 bits, you use EAX. And they did this for all the different registers here. And then came the 64-bit computers. Actually, before we get to the 64-bit, Intel at this point was kind of like, yeah, we're running out of names for stuff, and the architecture's kind of bad because we kind of put ourselves in a corner. Let's make a whole new built-from-scratch chipset. It's called the Itanium. And who's got an Itanium computer? Oh, like 2 people. That's awesome. Oh, well, they're dead. I mean, they're practically dead. They're not making them anymore, I believe. They stopped that. So AMD was like, hey, opportunity time. We can extend this. Not cleanly necessarily, but we can extend it. So they did. And now we have 64-bit registers, and they added a bunch of new ones. So I'll explain the naming scheme. Like, one thing that you'll notice is that all the 64-bit registers begin with an R. And R stands for register. Yeah, I kid you not, that probably won't age well either. But it remains to be seen. They just figured, look, for the new registers, let's just give them a number. Okay, so we have R8, R9, R10, all the way through R15. So that's like kind of sensible. And for the old registers, they're like, well, we'll just add an R in front, I guess. So they all begin with R, and that's how it works. But then they also wanted to provide you with like extra 32-bit registers and extra 16-bit registers and extra 8-bit registers. So what they did is you can add a number after the thing. So register 9 is 64 bits. And register 9 double word is 32 bits. Register 9 word is 16 bits. And register 9 byte is 8 bits. So that's why you see R9B, R9W, R9D. Now, does anybody know the word size of a 64-bit processor? I'll give you a hint. It's in the name. Yeah, it's 64 bits. However, because we're backwards compatible all the way to that 16-bit machine that we started with, the 8086, the word size when you're talking assembly is 16 bits. So we have this idea of a double word, which is 32 bits, and 64 bits is a quad word. And yeah, that's how we roll, okay? So you might look at this and say, man, things were nice back when it was the 8008, right? Does this feel familiar? I'll take your question in a second. Does this feel familiar to you? Like, have you ever been working with C++ for a little while and just like think about programming in C? Like how nice that was back when it was just C, you know, when things were simple back in the day. I don't know. I'm not making any judgment call. I'm just saying that you get the same feeling, right? You can kind of extend the complexity. And I think this is something that happens when you try to do backwards compatibility all the time. You end up with something kind of ugly that works. So question that you had.
No, I love the acronym for the instruction point.
Oh, I'm so glad you pointed that out because I was going to do it and I forgot. Yes, RIP for the instruction pointer. It's hilarious. Okay. Comment.
I think they're working on carbon-based processors. I think that says something.
Carbon-based processors. I don't even know what that means.
Because current ones are silicon.
Oh.
Graphene.
Okay. Interesting. I'm not sure what to do with that.
I don't know much about it, but
interesting comment.
I thought it'd be an interesting joke.
Wait, I don't get the joke.
Carbon, the successor to C++.
Oh, now I get it. Going up in smoke. All right. So, comment?
Yeah, it's just worth pointing out that 16-bit is the new 64-bit these days, because there's a new kind of processor where they want to do 16-point floating point operations for. Anyway, 16 bits coming back. It's
16 bits is making a comeback.
Yeah.
All right. Great. So now we are armed because we know what all these registers mean to be able to interpret the thing on that right, the assembly code that we were looking at. Kind of. Okay, so we start with our add instruction. Anybody know what add does? I'll assume you know, okay? So we're adding ESI and EDI, and when you're working with assembly code, there are two forms, and they both work in opposite ways, of course. We're using Intel syntax, which means the destination is on the left. Okay? And the way that you can remember that is that in C or C++, when you assign something, the destination is on the left. Okay? So it's just the same. So here what we're doing is we're adding ESI and EDI, and the result is going into ESI. Okay? So it's like ESI plus equals EDI. Now, ESI and EDI, we know what these are because these are 32-bit registers, part of RSI and RDI. Okay? We got our map, we know what that does. Great. It's adding things, like we said. This was adding 4 numbers together, this function. All right, now we're adding, wait, what the hell's going on here, right? There are 64-bit numbers involved. There is a 32-bit number involved, and Leah. Like, what does Leah mean? Okay, so if you don't know what that means, what you should do is you should look into the Intel i64 and IA32 Architecture Software Development Manual, Volume 2. So this manual is a behemoth, by the way. There are 5,062 pages in the manual. And just to give you a comparison, the C++ standard has 2,120 pages. But this manual is actually much easier to read than the C++ standard, so I'll give them that. And this is an excellent reference for Intel assembly. Like, don't try to find something else. Like, this is the place to go. It's good. And there's a PDF freely available. And what we're going to do is we're going to open up the absolute best PDF reader of all time, which is I get to educate you all because apparently you haven't tried the best PDF reader of all time, which is Adobe Acrobat. Okay? All right, so we're loading up Adobe Acrobat, and we go to this page, and we look up Leah. Leah stands for Load Effective Address. And I'm not going to read this because it's kind of crazy, but essentially what it does is it was an old instruction that you can use if you have a pointer to an array and you have an index into the array, like 0, 1, 2 or whatever, and if you want to compute what the memory address is of adding the index to the base pointer of the array. Load effective address. Okay? Okay, what does that have to do with adding numbers together? You may say, compiler, you are absurd. Okay? So it's taking RDX and RCX, adding them together as if one was the base pointer to an array and the other one was the offset to it, and putting the result in EAX. So there are add instructions, and they're using 64-bit registers instead of 32, but why? It's just weird, right? So here's your compiler looking at you, and I love this expression on the face. It's kind of like, what are you talking about? Like, stop. So anyway, your compiler tells you that's the only way you can do that with a 3-byte instruction. So this is how things work in assembly. If you're generating optimized assembly, you're going to get stuff which is very fast, it is not always pretty, and it works. So if you're looking at optimized assembly, you might get a strange instruction in there, and it's like, how does that have to do with anything? And you go and you read the semantics, and you're like, oh yeah, that actually works, but nobody in their right mind would ever write it that way. And that's how it does it. So coming back to our code, we see that we have ESI and EDI, which are being added together, RDX and RCX, which are being added together, and then all of these are added together into EAX here. And we can kind of see, okay, we're adding 4 numbers together and we're putting them in the EAX register. Great. But we still have no idea, like, how did these things get in that register? Like, why are we using EAX? Because this is it. This is the function call. That's the definition of the function right there. So So how do functions work? Well, the way that functions work is you set some memory and registers to argument values according to a particular calling convention, okay? You make backups of the registers that you don't want clobbered, and then you use the call instruction, which will put RIP, your current instruction, on the stack, and move over to the function that you're calling. And then when the function returns, it'll go back to that thing that you put on the stack to go back to the original place that you called the function from, okay? So calling conventions. There's more than one, of course. So here's the System 5 AMD 64 calling convention. And this is the calling convention that's used on Linux and Mac OS. And here we see, like, oh, the return value is using RAX. Great. And the arguments, you have argument 1, 2, 3, 4, 5, and 6 are these registers over here and these ones over there. And then you have argument 3, which can also be used as a second return value, which is interesting. So one return register is only going to give you 64 bits. But if you have something which is bigger than 64 bits, in theory, you can use RAX and RDX to return it without having to resort to using stack space or anything like that. So,
Is there an order to the return values, or is it just whatever you want?
is there an order to return values?
Is 1 higher than 2, or is 2 higher than 1?
Well, if you're only doing 64-bit return value, you'd use return 1.
Right. Now, if you had 128 bits, which bits go where?
Oh, which one's low and which one's high?
Yeah.
I would imagine, I don't know for sure, but I would imagine return 1 is low and return 2 is high. Now that we have this, we can look at our little function here and understand even more what's going on. Because we talked about EDI and ESI, which are part of RSI and RDI, which are, oh, this is argument 1 and argument 2. And then RDX and RCX, oh yeah, that's argument 3 and argument 4. And then we're adding them all together into EAX, which is the return value. So there you have it. Now you can understand what this simple function does.
Do you know why they chose to overload argument 3 and return 2 as opposed to choosing one of the other unreserved for the calling convention registers for return 2?
That's a great question, because that's kind of insane, right? I have no idea. Like,
it's because some of the instructions map with 2 outputs like that. So.
Don't they also try to keep the arguments low so they don't have to push as much stuff on the stack? Like there's rules about when you clobber the registers and when you can't, right?
hold on.
Are you getting there?
Hold on.
You getting there?
We're gonna get there.
Okay.
So it kind of looks like we have 2 32-bit arguments and 2 64-bit arguments.
Kind of looks like that, doesn't it?
Okay.
Yeah.
I think I recall something.
Doesn't work that way, but
Yeah.
yeah. All right, so there's a different calling convention you can use if you're using Microsoft Windows. And that's what this one looks like. So it still has the same return register being used, but it only has 4 arguments. So I guess you could think about this. If you go more than 4 arguments on Windows, you're not going to be passing by register. I don't really know how you use this information, but it's good to know. If you're running assembly for Windows, you got to follow this calling convention. All right, there's another aspect to the calling convention. And that is, what about the other registers? So this is hard to explain, so I hope I don't butcher it. But basically, if you get called as a function, okay? Someone called me, I am a function. I know that I can do whatever I want with RAX. I don't have to back up its value. It's mine, right? And that's what that up arrow means. That means that if I'm calling a function and I have some good stuff in RAX, I got to back up that stuff before I call that function. And the way you back it up is you push it onto the stack. So anything with an up arrow is the same as that, right? So anything with an up arrow, I don't have to back it up before I start using it and clobbering it or whatever. Now the things with the down arrow, like our BX, that means that if I get called and I want to use our BX, that has good stuff that the caller wants to keep around. So I need to back it up before I use it, and when right before I return from the function, I got to put the old value back into it. And the ones with the up arrow are called caller stored, and the ones with the down arrow are called callee stored. Did you all follow that? Because that's so hard to explain. Okay.
So why does argument 6 have a downward arrow?
Yeah, it seems really
It's the
weird.
only argument that does.
Why does it have a downward arrow?
Yeah, I would assume it to be caller stored.
There are two possible answers to that. One is I copied it wrong. The other one is it's crazy. Either one are equally valid. I don't know. Oh, no more questions? You were all thinking the same thing? That's hilarious. Okay. There's one other thing that I want to explain to you, one other instruction that wasn't in there, and this is move. Okay, move is how you move data between places. All right, so on the first line here, we're moving 255, the number 255, into register 10. Fair enough, easy peasy. Now here we're moving, this is brackets 255. When you see brackets in assembly, what we're generally doing is we're taking the contents of the memory at that address. So what this is doing is it's taking the contents of memory address 255 and putting that into R10.
So, yeah, I thought I had remembered that about brackets, and I had been misled by the previous example where we had the LEA with brackets around it. Was that just because there was a plus and that's just weird special syntax? Or
Yes,
okay.
just weird inconsistency. Yeah,
Okay, cool.
there's actually reasons for it, but complexity.
Okay.
Yep. Okay, now in this version of move, we're taking the contents of register 10 and we're putting that into the memory address pointed to by 255. And then finally, we're moving register 10, contents of register 10 into contents of register 11. All right, not too hard. I mean, kind of works. And there's no tricks to it, really. So now we have our full picture here. We understand how move works up on the right. And people in the back can't read that, of course, sorry. But I have an exercise for you. You are equipped to write the assembly for this function. Int main, takes no arguments, return 3. What is that assembly?
Yeah.
Wow, that was awesome. That was like a wave of the right answer. Huh?
Because we forgot to push all the callee safe registers.
Ah, but if you don't use them, you don't need to. So this is right. This is right. Yeah, good answer. You are a smart bunch.
We're advanced.
Very advanced. Okay, smarty pants. What is the output of this program? So we're taking argv of argc, casting it to a void, pointer, and printing it out. Who thinks that this is undefined behavior? Okay, I see 1, 2, 3, 4, 5. Who thinks that this is perfectly well-defined behavior? A lot of people. Okay, it's undefined behavior by the C++ standard. Okay? On Linux, this is defined behavior. Yes, it is.
Depends what, we had this bug. Depends what version you're on.
No, it doesn't. This is perfectly defined behavior, and what it outputs is, anybody want to guess? 0. Yes, great. Cool.
Null terminator.
We had to clear up our code.
Cool. So output 0. This is on Linux only. All right, let's do something else. Let's take argv of argc plus 1 and print whatever that points to. What's that going to do? Well, it on my machine it did this. That's crazy, right? Some weird thing.
Is that unit testable?
No. Because I tried it on our good compiler explorer, and I got this.
Wow.
Curious? So let's output more of these things. Let's see what we get. Huh. Strange.
There is a third
Oh my
argument.
god.
Third argument, anything else.
So let me do a loop and just print out all these things. What do I get? Whoa! Anybody know what these are? Environment variables. Yeah. So what the hell? Well, it turns out that when your program is loaded, there's a bunch of stuff on the stack. And one of the things that's on the stack is the environment variables. And this is how you actually get to them. Like, I kid you not, this is how you get to environment variables. So L floating. What's that?
There is another argument domain in V, which
Yes.
we normally get to them.
Yes. If you want to have non-standard Linux-specific code. Yes, it works. Yes?
So you said that it only does this on Linux.
Yep.
How do you access environment variables on Windows?
Well, the reason why I'm talking more about Linux than I am on Windows, aside from Linux being really cool in comparison, is that Windows doesn't document a lot of this stuff. Where Linux, we got full, like, good documentation. So on Windows, you use the APIs.
Use POSIX and learn. The C library has a way to do it. Just use C API.
Right, you can use the C API to get to it. But how the C API gets to it is through this stuff. So this is, when you launch a program, this is what you get. This is what your stack points to. This is called the L floating. And you'll notice that you have your stack pointer, right? And your stack pointer is RSP. That's your register that has your stack pointer to it. And the first thing in the stack pointer is argc, which is the number of arguments, followed by all the different argvs, right? And these things, because argv, remember, it's just a list of pointers, those things point to something way lower in the stack down here, which is your argument strings. Okay, so it points to all those things. Following the argv stuff, you have your environment pointers. There's a null in between, as we saw. And then all these things point into strings that are in your environment, which are also in your stack. And then, now we're getting super, super elite. There are the ELF auxiliary vectors. Yeah. And you can get to these by going through, using the same trick that I showed you before, the ELF auxiliary vectors. Like, what is that? So if you can actually see what's in the ELF auxiliary vectors, you can print them out using the trick, or you can call, when you start your program, add this environment variable ld show auxv, and you will see all the ELF auxiliary vectors that your program launches with. This is information you get launched with.
Can you return one slide, please?
Yep.
So is there anywhere the number of environment variables, or you have to look for the terminator?
You have to look for the terminator, yeah.
Are these all 32-bit pointers?
These are all 64-bit pointers.
I might be confused.
If you're running in a 64-bit mode.
It says size bytes 4 for each of those. It says they're pointers.
Oh, maybe this is showing 32-bit.
Okay.
Yeah. Depends, like, it's different for 32-bit mode versus 64-bit
It would
mode.
make sense.
Yeah.
Just a side note, is this a real definition? Because then the n at the argvn is somehow undefined because upwards it's just number of arguments and not n. So mathematically it's a bit unsound.
Okay, look. This chart on the right here, this ASCII chart, was written by two random people on the internet called GrugQ and Scott. So take it for what it's worth, all right?
So when you say Linux is better documented than Windows, that's a very relative.
Documentation exists thanks to GrugQ and Scud. Could not find out who those people are. Like, assuming they're people. Okay, ELF auxiliary vectors. You have a bunch of stuff in here. Like, there's some interesting things in here. You have UID, GID, effective UID, effective GID. That's all in there. Now you can actually get these through system calls, but they're put in here because it's faster to access them than having to go through system calls. A lot of the stuff in here is for when you're running an executable and it has dynamic libraries that it's linked to. Then over here, we have @random, which is a pointer to 16 random bytes. And this is used to implement a stack canary. So basically, this is preventing certain kinds of attacks when you're doing these like dynamic loads. Over here, we have a pointer to a page containing the virtual dynamic shared object. What the hell is that? The virtual dynamic shared object. All right, history time. In the old days, when you wanted to run a system call, and the system calls are generally elevated privileged calls, right? This is how you did it. You would move something into some registers through some calling convention. So here we have moving 1 into EAX, which is the exit system call. And then you have 42 moved into EBX, which is the argument to that system call. And you'd call this assembly instruction called int, which stood for interrupt. And interrupts were designed so that you have hardware interrupts and you have software interrupts. Hardware interrupts are basically a mechanism. So if you have a computer and it's using a NIC card or something like that, and it gets some data from the outside, and you want to tell the CPU, stop whatever you're doing because something happened, and go run this interrupt handler code, and then you go back to it. Okay, that's what interrupts were designed for. But you could also do software interrupts, and that's what's going on here. We're launching a software interrupt, interrupt 80, and the operating system sets up some kind of table of information to be able to do certain things based on whatever your system call number is. And this is how things used to be, and they were slow. And this is all by convention of whatever your OS is. So Intel said, hey, we can do better than slow. So they created sysenter and sysexit. And AMD, in parallel, said, we can do better, and they made syscall and sysret. Two completely different ways of solving the problem. They weren't talking with each other, so now we kind of have both. So in 32-bit mode, interrupt 80 works on Linux. But sometimes sysenter works, and sometimes syscall works, depending on whatever CPU you're using. So the Linux people were like, okay, we want to use these new things, but we don't want to have people have a different compile of the kernel or of all your applications, actually, in order to be able to use one or the other. So what they did is they created the Virtual Dynamic Shared Object, VDSO. So what this is a dynamic library that's linked to every executable that in Linux. You have this dynamic library linked to it, and you can see like LDD on this, you'll see something VDSO. And what it does is it provides one function. And that function is __kernel_v syscall. And you can call that function from that dynamic library, and based on your CPU architecture, it will run the right syscall mechanism to be able to run the system call. And that's what the virtual dynamic shared object, that's why it got created. That's what it is. Any questions so far? Does that make sense?
Does the cost of the call queue before the faster dispatch, like how does that add up?
It adds up to faster,
Okay.
yeah. Otherwise I wouldn't have done this. I don't actually know that it's faster. So then the kernel people thought, okay, that's actually kind of neat. We can like inject a whole bunch of APIs in user code, in user space. What kind of things can we put in there? And they thought, and they were thinking that like some system calls are really expensive, but they don't need elevated privileges. Like if you're getting the time of day or whatever, you don't need elevated privileges. This is just reading memory from somewhere. So they were like, okay, let's add more stuff into the virtual dynamic shared object, VDSO. And so they did. And if you look at the man page for VDSO, you'll be able to see a list of all the things that they put into every single executable that are basically system calls without having to get elevated privileges. So here, when we're looking at 8086, here's the list of system calls that you got. And here we have vsyscall, right? The kernel vsyscall, this is the one to be able to use the right thing to make a system call. But then you also have these clock functions, get time of day, time, and these are way faster than calling the corresponding system call, because it's just reading memory. Now, if you look down to 64-bit, you'll notice that that vsyscall thing doesn't exist. Because in 64-bit mode, you don't use that to run system calls. We'll talk about that in a second. But they still thought it was a great idea to have this thing because you have these fast system calls that don't require elevated privileges stuck in there. I just think this is interesting. I don't know if you're going to take away anything from this and do anything different, but it's curious. So x86 64 syscalls. So here we have a snip of assembly, and what this is going to do is it's going to output hello world and then exit. All right, that's all this does. We'll work through it. We got this thing. At the top of the file here, we have some constants. Right? This is basically just a convenience feature of this assembler where stood out refers to 1, sys right refers to 1, and sys exit refers to 60. Okay, they're just constants. That's all that's there. And then we have a data section, and here we have this data, which is hello world, and we're calling that string. Okay? Question?
This is an ELF file.
This is a what?
Is this an ELF file?
An ELL file?
ELF.
An ELF file? Well, this is an assembler. Yeah, this is an assembly language file.
Okay.
Yeah, that you can assemble into an ELF file. And now we have our code. And what this snippet of code does is well, let's work through it. So the first thing is we get the size of the string, which it files at assemble time, it figures out at assemble time, and it moves that into EDX. And then it looks at the offset of the string, which is the length of the string, and puts that in RSI. And then it takes EDI and it puts stood out there. Remember, stood out is just 1. And then EAX, it puts sys right, which is just 1 as well. And then it executes the syscall instruction. And by this convention, what happens here is this will call the right syscall, outputting hello world to standard output.
Just to make it clear, so string is a name, not a type.
I know, it's kind of confusing, this example. Yeah, it's just a name, it's not a type.
Okay.
There's no types.
What's the DB in that case?
What's the DB? I'm not sure.
What's the 10?
What's that?
Define bytes.
Defined bytes? Could be. Yeah. I don't actually know.
What does the 10 mean?
What is what?
The 10. Hello world, comma 10. It's not the red.
It's like a 210.
All right, this is me waving my hands. I don't know. You'd have to look at the instructions to the assembler, which I didn't use. This is an example from their documentation.
What was the offset string?
So offset string gives you the length of that string.
Isn't that what size of string does?
Like size of, yeah.
But size of is underlined before.
Wait, what the hell? No. Hold on. I said that wrong. Size of is the size of the string, yes. Offset of the string is the address of it relative to this current location or something like that.
DB is defined bytes, and you can define words and other things too.
Thank you. Yes. Okay. Forget about the stuff above that I don't understand. Do you understand this part at least? No. Okay, good. All right, the next part, we're moving sys exit to EAX, which was the same place that we put sys right. So this is obviously in this convention where you put your syscall number. And we run the syscall, and that exits the program.
Where do we put the exit code?
Where do you put the exit code? I don't know. I'd have to look at the calling convention of the system calls for Linux to figure out where that argument goes. Yeah, it's kind of surprising that it's not in this example, like a 0 somewhere. But I don't know. It's one of these registers.
So is syscall now unified between AMD and Intel architecture?
For 64-bit, syscall works on both. Yeah.
So before we saw main using move EAX, the return value, and then ret. I'm assuming it's because this would typically call main.
Yes.
There's no main.
Well, if there was one.
Start jumps into main usually, but we don't have it.
Okay.
Right. Yep. And if there's time, I have some bonus stuff that will go into like how main is actually called. All right. Any other questions or comments? Okay, we'll take these two and then move on.
Is the end start necessary, or like, is it something that's executed at all, or is it just there for completion?
This is, yeah, for the assembly, the opposite of underscore start, right? It's like that, that's tagged. And then the assembler will use this to say, yeah, this is where you're actually starting. All right, the question over here. Oh, same question. Okay, great questions. Next time I give this talk, I'm going to study up on the assembler so I can answer these ones. Okay, so when you're doing syscalls in Linux, you should prefer to use GNU libc. Just use your C library. 99% of the time, that's all you need to do. Don't worry about doing syscalls. However, glibc does not include every syscall that Linux provides. And sometimes it takes many years before it gets into glibc. And sometimes it takes infinite years because the glibc just says, look, we're the GNU operating system. We don't want to be Linux specific because people might be using herd. Who's using herd? Nobody. Okay, that's what I thought. But they want to make a general thing. They don't want it to be specific to a kernel. So if you want to call some of the new stuff that comes out in your next kernel version and they added some cool syscalls, there's a function called syscall that's part of glibc that you can use to execute those syscalls. Now let's say you don't want to use glibc. Glibc is a bloated mess, right? Well, there's this thing that comes with the kernel called nolibc. And it is an absolute minimal like C library that calls syscalls underneath the hood. And it's super cool. So if you want to make an executable and you want that sucker to be like dinky, use nolibc. And it's on all the Linux computers because it comes with Linux. Just fascinating. All right. Let's talk about atomics. So there's this quote from Fedor, who's in the room, from The Art of Writing Efficient Programs. And I love it. Developing lock-free code may be cool, but trying to find bugs in it is most definitely not. Now, what I want you to take away from this is that developing lock-free code may be cool, so let's try it, all right? All right, so here we have a set function. We're not using atomics or anything like this. And it takes in a reference to a value and a reference to an is-ready bool. So this is like, we'll see how this is useful in atomics in a second. So we set the value to 42, and we say is-ready equals true. What does the assembly look like for that? Well, it looks like this. This is kind of something that we can understand. We move 42 into whatever RDI points to. So this is the first argument. Yeah, the first argument is RDI. And it's a pointer because references are basically pointers. So whatever it points to, we want to set that equal to 42. And D-word pointer, you can just ignore that for now. And then we move the number 1 into whatever RSI points to, which is like a byte pointer. And then that's basically is ready equals true. Make sense? All good? It's great. All right, so now let's do it with atomics. Okay, so the idea of this set atomic is you set your memory to something, and then you set this atomic equal to true, and something else could be doing a spin lock, like waiting for that atomic to say that, hey, the thing is ready, and then they can read that memory value. The way you do that is when you store true into is_ready, which is an atomic, we use memory order release. And that basically guarantees us that that value equals 42 won't get, like, by the compiler put after isReady.store, okay? Keeps it there. All right, let's see what the assembly language looks like for that.
Really?
Remember the first thing we learned about assembly? It's the same thing, right? You don't have to know assembly. This is the same thing. That's weird, right? Okay, let's look at the other end of this. This is the get. You have your value reference and you have your is_ready bool. If is ready, return the value, else return 0. So this could be the thing that we call over and over and over again to see if in a different thread to see if that value is good to start consuming. So we look at the assembly for this. Okay, the first thing that you'll see is XOR EAX, EAX. This is just the compiler being insane again. But if you XOR anything with itself, you get 0. Okay, so this is just a efficient way to set the EAX register to 0. Now you could set it to 0, but that'd require more instructions. It'd be like longer, so the compiler's like, this is the faster way to do it.
Couldn't you EAX 0?
Yes, you could do that, but that won't be as efficient as this. This results in fewer bytes of machine code instructions. Yeah. Okay, so the next thing we do is we compare whatever RSI points to, which is that bool, to 0. If it's equal to 0, then it jumps to the bottom and just returns. Otherwise, it moves whatever RDI points to, which is the value parameter, into EAX, which we remember that's the return value, and then it will return. Okay, straightforward.
You might have already explained this, but the byte pointer and dword pointer, they don't seem like part of the instruction. Like, they don't seem like a part of the argument to the compare assembly function. Like, what do they represent?
So this is just talking about the way to address what this thing points to. It's like, this is a byte pointer, this is a double word pointer, which is 32 bits.
They're qualifiers on the first argument to compare.
Exactly.
Okay, thank you.
Yep.
Again, the compiler knows you're storing 0, which can be represented with one byte, but the input value doesn't know how long it is, so it uses a bigger instruction.
If you had the other assembler, it would say move L and CMPB,
Right.
where the suffixes denote the length.
Yep. Question in the back?
Yeah, the question is why is the XOR not just in front of the red? Because now we store 2 times in EAX in the success case.
So, I mean, I guess you could do that. Like, I'm not going to argue with the compiler because it usually knows better, but I mean, you could. Okay, question over here.
For dword pointer, is that what alignment is?
That's not alignment. Alignment is different. Yeah. Okay, let's look at the atomic version of this. Okay, the atomic version is the exact same, except when we query our isReady.load, we're using memory order acquire. These things need to go in matches, and this isn't the talk to explain how atomics work. Trust me, that's the right way to do it. Now let's look at the assembly for that. It's different. Okay? The first instruction here takes whatever RSI points to, which is our pointer to the bool, and move Z X's it into ECX. Okay, so this is just like a move instruction, but it zeroes out the first part of the 32-bit, right? Because we have a byte, we're moving into the register, and at the same time clearing out, putting zeros in the front side of that register. That's what that's doing. Then the rest of it looks kind of the same, right? We do EAX, we set EAX to 0, then we test CL for 1. Remember, CL is the 8 bits, the low 8 bits of the RCX register, right? And then we jump if it's equal to 0, and then if it's not equal to 0, then we go ahead and we make that move of RDI into the return value, right? We move the value argument into the return value. Okay? Oh, lots of questions. All right, go ahead.
So do you know, like, does move ZX actually have any different ordering required, like guarantees, or is this just because this is now a template and for whatever reason we're getting some noise out of the class itself?
Like, could we have done this without MoveZX?
Yeah.
Probably. I'd have to think about it. I'm not sure.
Because Intel's pretty coherent to start with, so I was, just curious.
Yeah.
So that first instruction, we are loading 1 byte into ECX, quote unquote. But that's technically just loading it into CL, which is one we test later.
Yeah, it loads it into CL, which we're testing later, and it zeroes out the front of that.
The rest of it, okay.
Yeah. I'm not sure why. It could be because it's shorter than just moving the byte over to CL.
Some sort of backwards compatibility thing.
Probably not backwards compatibility. I think it's more likely to be efficiency for instruction size. All right.
The top one is checking if the argument is 0, but the bottom one's checking if the argument is 1. That's kind of confusing to me.
It also uses a different instruction for some reason. No, that's the true. That's the if.
Right, but
Yes.
in one spot it's checking if it's false, and in the other it's checking if it's true, right? Because one it's comparing
No, test
the
and
value to
CMP,
0.
test and CMP are different things.
What is
Test,
So that's what I'm asking.
CMP actually does the real comparison and then sets the status bit. And test actually checks the status bit. So the test and CMP checking different things.
Test is basically aimed.
Oh, right. Yeah.
Test is
They're different instructions, but they're getting the same result.
They're getting the same result, but what they're looking at, there is like an invisible bit that happens after every instruction and it checks whether or not the result was 0. And test looks at that bit and sets it into CL.
Doesn't test do the subtraction and then set the 0 bit because they were
Yeah, but it looks at the status bit of the last instruction.
compares the subtraction. Test is an end.
Yeah, test is an end. Yeah.
All right. I'm gonna move on because this is all really interesting. But there's a point to this. So basically, when we're talking about atomics, moving 1 into something that's pointed to a byte is atomic, apparently, right?
On x86, we heard here.
We're talking x86. This is all x86. Now, if we do this CMP function where we're comparing 0 to something that's pointed to by RSI, that apparently is not atomic. Otherwise, they would have reused it in the second version. And then this MoveZX instruction is atomic. Now, none of these instructions have a lock annotation to the front of it, which is the way that normally in Intel architecture, you put a lock in front of an instruction. Now it's an atomic thing. But like, what's up with that? And then we have atomic code, which looks the same as non-atomic code. What's going on here? Let's talk to our compiler. Compiler is always grumpy. Anyway, what she says this time is that maybe you should read the manual. All right, thank you, compiler. So we'll open up our manual here, crack it open. This time, volume 3. Guaranteed atomic operations. So the Intel 486 processor and newer processors since guarantees that the following basic memory operations will always be carried out atomically. Reading or writing a byte, reading or writing a word aligned on a 16-bit boundary, or reading or writing a double word aligned on a 32-bit boundary. So basically these instructions, these move instructions, are called out under these circumstances as being atomic. So let's go back to this quote. Yeah, trying to find bugs in this is just not cool. So let's not do this anymore. All right, so I want to talk a little bit about CISC and RISC, okay? CISC stands for Complex Instruction Set Computer. So the Intel x86 stuff, that's a complex instruction set computer. You have instructions which do a bunch of things at the same time. And then there are RISC computers, which are like ARM, newer Macs have this, Raspberry Pi has it. There's a lot of stuff, there are a lot of RISC processors out there too. So let's look at an atomic increment on an x86 processor. So here we just take some atomic and we do plus plus on it. And the Intel x86 assembly for this, there's just a single instruction which does all this. It does the loading, it does the incrementing, it does the storing, all atomic, all in one thing. Now, what if we want to do this for ARM? What does it look like? Well, for AArch64, you have a label here, and then you do this atomic load of your memory address. So this is a different assembly language, but it kind of works in a similar way. Whatever X0 points to, the contents of that, we move it to register W8, okay? But we do it in atomic read. Then we add W8 to 1. So destination W8, two sources are W8 and 1, the constant 1. Then we do this, which is stores the result, stores W8 back into X0 atomically. But we get back some information in W9 which tells us whether or not that atomic store succeeded. And if it didn't succeed, then it will go back and loop. So this essentially loops until the atomic store is successful. Like, this is actually not very efficient. Comment.
So this the C++ code is now a sequentially consistent operation rather than a release. Would it look similar?
Like with just
like I'm trying to get a feel for what's coming in because of sequential consistency versus what's coming in from switching to ARM.
I don't know.
Okay.
Yeah. Okay. So this is kind of crazy. So the people who make ARM recognize this as a problem. So in ARM version 8.1-A, they came up with a new way of incrementing incrementing an atomic. Now, the old way, because they did this because they really want to have these simple instructions, the smallest number of instructions that you can use to build up everything. So what they did is this. Move 1 into register W8, and then call load add all. Load, add, acquire, long. Which is kind of hilarious when you think about it, because they just went with a complex instruction set for this thing. Good business decision, but didn't really align with the methodology there. Okay, so on modern Intel CPUs, there are actually over 556 registers. I only showed you some of them. I showed you the general purpose ones. There are things for segmented memory, which was brought up before, which obviously I need to read up on. There's SSE, AVX, there's debug registers that you can use, and there are over 2,000 different instructions. So of all these 2,000 instructions, what's the craziest one? Well, I'll show you the craziest one that I'm aware of, okay? It's the pulcum-emsturm function. Now, what this stands for is packed compare explicit length strings return mask, which doesn't help, okay? So let's talk about what this thing does. So basically, you have two strings, okay? They're packed in these MMX registers, these AVX registers. Basically, they're a single register that holds multiple values. It's like an array, but held in a register. Okay? And it does comparison operations between these two things. So the first argument is one of those crazy registers, the second one's another one of those, and IMM8 gives you some kind of like control over what this crazy thing does. And the result is put in the first XMM register. Okay, fine. RAX and RDX are the length of the first string and the length of the second string. So this is one of those instructions that picks on particular registers to get some information from. And then IMM8 is the comparison. And the different bits in that thing control what this thing does. So bits 0 and 1 specify the data type. Is this a list of uint8s, uint16s, or int8s or int16s? That's what that does. Now bits 2 and 3 specify what the operation does, and there are these four options. So subset will, what it'll do is it'll take the first one and interpret it as your string, and the second one it interprets as a set of chars, And for each char in the first one, it'll tell you if it's in the set in the second one. And whether or not it is or it isn't, it'll have a 1 or a 0 in the resulting mask that you get out of this thing. And then there's ranges, which is even crazier. So the second one, okay, so let's say we have an example here. The first thing on the top, the too cool thing, that is our input string. And the second one is a list of ranges. So to interpret that as like the range from A to Z, lowercase a to lowercase z, and the second one is the range from uppercase Z, A to uppercase Z. The resulting mask will tell you for each one of those characters if it falls within one of that set of ranges in the second one. So all the things that are not letters in this example get a 1 in the resulting mask.
So that implies that the string has to be an even size, the ranges string? Like it has to be a pair of start, stop.
Yes, correct. Oh, or maybe it's defined if it's not. I don't know. But that's the only way I know how to interpret it.
On the previous slide when you said there's like 556 registers, do you know if that's before or after register renaming? I'm just kind of curious.
That is like before.
Before.
Yes. And then you also have match, which will do string comparison. There's a substring search. All this baked into your Pookem function. All right, and then that's not all. There's more. You can complement the result if you want the mask to be inversed. Or you can complement only the valid bits, whatever that means. And you could decide if you want to get bytes as the output, or if you want it to pack as like bits 0, 1, 0, 1, 0, 1, as opposed to a byte with zeros and ones put into the resulting vector thing. Isn't that great?
All of the bits worth it.
I guess, yeah, for future use.
You use the wrong compliment. You're telling it that it's really nice instead of inverting the bits. It's misspelled.
Oh, I had a misspelling.
Compliment.
I love it when people point that out in front of everybody. Thank you.
How often does that instruction appear in actual?
How often? I didn't grep for it. I'm thinking somewhere between 0 and like 0-ish.
Comment, the intrinsics guide puts this at 19 cycles latency, but 4 cycles per instruction throughput.
Okay. Information. Okay. Let's move on. How much time do I have, by the way? Well, you look that up.
23 minutes.
23 minutes. Okay, we might have some extra time for bonus stuff. Okay, so there are cool things to explore that I'm not covering this talk. Concurrency, actually the model for like Intel CPU, Intel didn't actually provide it. They just provided a bunch of examples. And some researchers went and they created a model for it called x86 TSO. And then if you read that, then you can actually kind of understand, oh, here's a mental model for how these different instructions work. So that's kind of neat. Segmented memory for future. IOU ring is a very cool set of Linux system calls that I think are going to define the future of what system calls are going to look like. There's return-oriented programming, which is basically some neat hacker tricks you can do if you know assembly. Instruction pipelining, micro-benchmarking, these are all things that I'm not going to talk about, but you will be very excited after this talk to go and research these things. They're cool. I have resources for you. Obviously, you're not going to click this because it's on the screen in front of you, but I'll put it in the chat, the link to the slide so you can go to these. If you want to learn assembly for real, Creel's assembly tutorials are awesome, and they're hilarious. This is where I learned it. I highly recommend that. Of course, you got your software developer manuals from Intel. There's an online assembler that I use that also does disassembly. So if you're wondering, why did the compiler do this as opposed to this other thing? You paste the little assembly code in there, and then you can see like, oh yeah, because this instruction is like twice as long in machine code. Agner-Fogg has Agner-Fogg's optimization page. If you're doing anything with assembly, this is like part of your bookmarks. It's so many resources coming from that. If you want to learn more about why, like the evolution of how AArch64 got atomics that were kind of CISC looking. That article is for that. And finding out how many registers are in an Intel processor is a non-trivial thing to figure out. So this page gives the work behind the number that I used to try to compute the number of registers there. Linux resources, we have VDSO manual, which you've seen. If you want to hear the controversies between the glibc people and the system call people, there's a LWN article on that one. And then this thing, this is the assembly code that launches main. And it is so cool. And I've got some bonus slides for that. So let's take a look. Okay, here it is. Here it is. The assembly code that calls main in C or C++. So remember, when you get started, you get that stack with all that stuff in it, right? So the first thing that we do is we pop the top thing on the stack, remember that's argc, and we put that in RDI. RDI is the first argument register, right, for when we ultimately call the main function. And then we take RSP, so this is the stack pointer, whatever is there, which is after the argc, which is the first of the argvs, we put that in RSI, which is the second argument to main, right? All right, then we do this. So what this is doing is we're taking RSI plus RDI, so that's the argv plus argc, which brings us to the end, plus, that should be 8 there, sorry, that was my mistake, plus 8 to get past that null pointer, and that gives us the pointer to the environment variables, right?
Instead of a multiplication sign, it should be a
No, this should be in multiplication sign because RDI argc is in like which index.
what is the mistake?
The mistake, this +1 should be +8.
Oh.
Because pointers are size 8. That's why we're multiplying by 8. And then what we do is we save RDX, which we just computed, into environ. So imagine this is like some static variable which is available. This is where like libc will get the environment pointer from. All right, then we zero out the stack frame. And this loop searches for the auxiliary vector, right? That cool thing. Once we get that, we save this into _auxv. So this is again like some kind of global variable that your libc will be able to access to get to the auxiliary vector to be able to do all the magic stuff there. Now if you're on the x86 ABI, which this is, then we need to make sure that ESP, the stack pointer, is 16-byte aligned, okay? And the way that we do this is we take -16 in binary is, I believe, 11110000. So what this is doing is taking RSP and just clearing out the bottom 4 things to make sure they're all 0, so that we get the right alignment of our stack when we call. And then we call main. This is where it happens. So it calls main after setting those registers to the right thing, so argc and argv point to the right thing. Once main exits, we know that the result of main is going to be in EAX, right? That's the return code thing. So we put that into EDI. We put 60 into EAX, which is the system call for exiting. And then we call syscall to actually exit the program. And that's how it works. And then there's this thing, which I have no idea what it does. but apparently, and actually for some loaders like this doesn't exist. But presumably you never get here, and this is like some kind of emergency extra thing that they put there.
Probably use halt.
Well, halt, yeah, for sure. Yeah, I don't know what the semantics are. I could kind of guess what it does. All right, I see a hand up in the back there.
At which point is gvec initialized?
At which point is what initialized?
gvec. So you have like global variables that need to be initialized, like especially in C++.
I'm not sure. I'm not sure how that part works. Oh, wait, hold on. This loader is that no libc loader.
Okay, right.
So there would be none of that. So glibc will have a different loader thing like this.
Have you ever been annoyed that main takes like ints and pointers and thought about making like a C++ range friendly main for yourself? Have you ever tried something like that?
I have not, but I know people have tried, and they brought it to the committee and didn't work out. Okay.
Yeah, I was just curious. So the OS itself then has set up the stack for us here in advance, and we're just kind of getting things ready so that to main it looks like these things have been supplied as like normal arguments. It's just kind of odd that like if the OS has already set up the stack for us, why do we have to make sure that it's like 16 byte aligned? Like it's just odd that the OS itself wouldn't have done that. Like,
So it's part of the ABI for C++ and C.
okay,
right?
so it's not okay. So if we were using some other ABI, conceivably, I guess it would.
Or some other language.
I gotcha. Okay.
Yeah.
Actually, not the OS, it's the shell, which is just another process, right?
Right. Okay.
I mean, shell isn't any particularly privileged. It's just another program.
Right. Right. Well, so okay. So when it forked, I guess then that stuff was already on the stack at that point. Is that what you're saying?
It did well.
When
no,
exactly?
well, it didn't. It didn't. I mean, it executed at some point. Yeah.
Mm-hmm.
Yep. Called a syscall to fork and do that kind of thing. Question.
So when we do the zeroing out the low bits of the stack pointer, that's moving the stack pointer earlier, but there could be stuff there, right? Do we care, or are we just like we're gonna write over that and like?
The stack goes down, we're done
So we're moving it.
So we're.
Yep.
So is this just a program that calls only main? Because what would happen if I had static variables with constructors and destructors? Would this appear in that code? The add init, add exit stuff?
I think it says called nullity. I don't think nullity is a cause now.
Oh,
Like
nullity, no static variables.
no, like
With
static
the
variables, so
constructor.
you have to be constant initialized anyway.
Okay.
Okay. I'm so glad these questions are being answered in here, especially the ones that I don't know. All right. Well, this is the end of the talk for real this time. So now we can take questions and comments.
So obviously, like when people were writing, like there was a time when people were writing assembly code, right? Like they were handwriting. Yeah,
I was there.
Yes. But subsequently, there have been developments of like a multitude of abstraction layers that kind of obviate the need for your run-of-the-mill software engineer to have a concrete understanding of assembly. And aside from compiler authors, I'm curious, like, what do you think are the really cool benefits of like having a fundamental understanding of how assembly code works? Like, what types of engineers benefit from that? Like, what kind of extra information can be gleaned in like our development, like our day-to-day development practices?
That's a good question. So I think that the use of this information is completely non-useful for most of anybody's career. But then there will be a moment where this understanding will make something possible that nobody else thinks is possible. Right? So this Sean, I see you raising your hand like you want to say something about this.
Yeah, I was going to say two examples. One is this is incredibly helpful if you're stuck debugging something that you don't have sources for example, and you need to trace through it and figure out what are my arguments and where are things going wrong. So that's a very practical use case that comes up a lot. You have to debug into Mac OS or into Windows or something because something's going wrong. Here you can help figure out what's wrong with my arguments, type of stuff. The other piece is when it gets down to trying to optimize code. Like, I don't know, Nick DeMarco is here. Nick and I did some work on Bresenham's algorithm, which is a line drawing algorithm. And turns out if you know what you're doing and you know how the arithmetic works out, you can eliminate one branch. And so we could draw lines with no branches, which means that they can vectorize, which means that you can execute them on SIMD. And that's just knowing how math works on these processors, and that there's an adequate carry, and you can capitalize on that carry bit to eliminate a branch. So having that deep understanding doesn't come up very often, but every once in a while, you know, if you can draw lines 15% faster in your graphics application, that's a pretty big deal. So.
And I have a third example. It's the only choice you have to actually prove that you have a compiler bug. I mean, this comes up rarely. We often think it's a compiler bug, it's our bug.
It comes up more often than you would
Yeah,
imagine.
but it comes up, especially if you're programming like on the leading edge of C++, there's a surprising number of code generation bugs in Visual Studio or also.
Yeah, I was gonna bring that up. The large scale code changes, you hit code generation bugs, and often essentially the last resort. Short of like having a minimum viable reproduction that should clearly just work, like you have to, and sometimes you can't get that. Like so, you take the snippet of the assembly output and show why it's like you clearly didn't set the return value, and then you returned. And
you do often it's simple things like taking the address of a variable instead of its value.
Right.
This is kind of a subcase of the optimization, but it's certainly important to my growth as a programmer. It helps me not be the guy who's confident that if I stick parameter on my addition, that it's faster just because I measured it to be faster. I think, like, that's a real thing. Like, I'm confident that I can change my C++ code and this is faster, but wait, the assembly's the same. No, it isn't.
Yeah, in general optimizations, I don't know, like how many, like in your organizations, like, do you have arguments about whether you should check for null before calling delete? Like if P not equal null, delete P.
We don't. We have very few run moves and deletes.
Well, somewhere it's in there, right? But like usually you.
It's not something I deal with.
It's somewhere at the bottom. So you could actually, there's like a lot of arguments, whether on one hand, like, is it redundant, but the branch predictor is primed already and so on. You can look at that assembly and find out that it doesn't matter.
Well, you have to be careful though, because like the assembly will change a lot based on flags, and so like if you look at the assembly, look at all the assembly.
Well, yeah, all the relevant.
One like godbolt snippet is great, but you might need like 15 tabs to really hit all branches. Right?
Yeah, but some things you can really like find out, or the other one is like
Well, you only need one example, but like to prove that it's fast or something, you need to really hit the thing, at least the parts you care about. Right?
You're doing some work that you think like will help your code vectorize. So you are rearranging, you are removing branches, but did it actually vectorize or not? Okay, you take that function, like it may or may not even run faster. That's a different story. If it's vectorized but it doesn't run faster, then okay, you have to figure out why. But you would actually see whether or not it's vectorized.
Right.
And the vectorizing compilers are, the decisions they make are not obvious about what they can and it's not what could be vectorized. It's more about what they know how.
David gave a whole talk about what the compiler does. It's not always obvious at one of our meetups in New York.
Yep.
Title?
Thanks for the plug.
What was it called?
I'll look it up.
The semicolon is a line.
The semicolon is a line.
Semicolon is a line.
Yes.
So we can get that.
One comment, just because Dave showed that, with or without an atomic, some functions are the same on x86. Intel actually hates that they have to do that, and they have to make those things atomic because people used to use volatile to mean atomic, and that's not what volatile means. And it just turns out on the old chips before you had cache architectures and stuff, what that meant was stored in memory, and that itself used to be an atomic operation. But that comes at a high cost on Intel, and that is not true on other processor architectures like ARM or PowerPC or MIPS or pretty much anything else on the planet. And increasingly, even on Intel processors, if you turn on things like auto-vectorization, the compiler will generate different instructions that are not atomic unless you say atomic. And that will burn you. So if you need an atomic, say an atomic, even if the assembly language looking in godbolts is the same.
Even in that example, the compiler could have generated CMOV.
What's that?
Even in this example, the compiler could have generated CMOV for the conditional return instead of COM. And which wouldn't have been atomic.
Yeah. And so just serious word of caution from somebody who spent a huge amount of time debugging all of those issues as we went from Intel to ARM.
And another example is like if you have to track down UB. So like you can find this example in my book where like UB actually crashes your program before it happens. It has to do with like a pointer that is being dereferenced, so it's definitely not null. The compiler deduces that it's not null, looks up the last place where it could have been null, optimizes away all your checks for null, which were there. So you wrote if p, star p equal 1, and then somewhere down there you said plus plus star p. Well, the compiler looks and says there's no way to change p from here to here. If it was not null down there, it must be not null up here. I'll remove this redundant if. I mean, you're going to crash one way or the other, but you're going to crash on the first use of pointer instead of the second one, even though you protected the first use in your code. And you see in the assembler that the check is gone.
All right. Any other answers to Kristen's question?
Anything that involves David.
Any other questions? All right. Well, I love it when that happens. Go ahead.
I'm still sort of hung up on that crazy PCM Intel instruction. Do you happen to know the historical reasoning behind it? Was it just like some engineer was bored on the weekend or something?
Well, I don't know the answer for that particular instruction, but when they first started doing these things, they were called MMX, multimedia extensions. And if you had a chip with MMX, it made you feel like, computers with like audio, like really advanced stuff. But they were things like this, and I don't know. Someone must have had a use case for it.
Yeah, I was going to say, having gone through chip design, because I worked at Apple and transitioned from 68K to PowerPC, so we had lots of arguments with IBM about the instruction set for PowerPC and what came out of Power and what got added. A lot of these things are just like the vendor has a particular customer who is going to buy X number of machines, and they create database systems, and this will be faster. And so, if you have very deep pockets and you're a very big customer, you get to buy your own instruction. is kind of how that works on a lot of these things.
Is that like giving a star after your wife or something?
Yeah. I mean, it's fun if you go look at different instruction sets. Like one of the instructions on a PowerPC is named EIEIO. Which was a bit of a stretch to kind of get the acronym to lay out like that.
Do you recall what it stood for?
I do not. I should, but I do not. You can look it up, I'm sure.
All right. See no more questions or comments. Thank you all very much.